Flipped classroom video for Maths AS Unit 1, the remainder and factor theorems. So we looked at addition and subtraction and multiplication of polynomials in the previous video, but now we're going to look at division of polynomials, which is a rather more complicated job. And to take us into this, we're going to look at long division of numbers, which you already know about, but just a bit of a reminder. So we're going to look at 456 divided by 13. And of course we'll use a calculator for that in normal times, but if we had to do it by hand, we might write it out like this. So 13 into 456, sometimes called the bus stop method. And the first thing we do is we say that 3 13s are 39, and that's the largest multiple of 13 that would go into 45. So we put the 3 up at the top, we put the 39 there, and that means there are 6 left over. It's actually 450, take away 390 if you think about place value, but either way that leaves us with 6 or 60, and then we bring the 6 down, so that 60 becomes 66. We then think about how many 13s will go into 66, and in fact that's 5 13s is 65, so we have 5 up at the top there for the answer and 65 there, and there is 1 left over, and we might write that as remainder 1. So we could say that 456 divided by 13 is 35 remainder 1. So that's written there. Now in fact that 1 is not a 1, it's a 1 left over, but if we actually had to divide that as well, then we could carry on into decimals, or we could say that's 35 and 1/13th, because the 1 hasn't been divided by 13 yet, and so by making it into 1 over 13, then that is the same as dividing it. And that tells us that the overall result could be written as 456 is 35 13s plus 1 left over, if you like. So if we were actually sharing 450 sweets between 13 children, then they would get 35 each, and there'd be 1 left over for the teacher, for example. Okay, so now we've seen that, which we may not have seen for a while, but hopefully remember, we can now have a look at long division of polynomials. So polynomial division is done in a similar way, or can be done in a similar way. There are various ways of doing it, but I want you to have a look at this way. So we're going to think about how to divide x cubed plus 5x squared minus 2x plus 6 by x plus 6. So we set it out in the same way as we did the other division. Now, what we have to think about here is that the x is the higher power for the polynomial we're dividing into the other one, and x will go into the highest power we have in the polynomial, which is x cubed, and it goes into x cubed x squared times. So x cubed divided by x is x squared. So that's going to be the first part of our answer, but just as before, when we had 13 and it went in 3 times, we had to do 3 times 13 and then subtract that. This time we have to do x plus 6 times our x squared, which gives us x cubed plus 6x squared, and we have to subtract that. So that gives us minus x squared, and then we bring the next term down. So now we've got minus x squared minus 2x. Now this time the highest power for what we're dividing into is x squared. The highest power for our divisor is x, so that's going to be x times minus x. So we do minus x times the x plus 6, which gives us minus x squared minus 6x, and again we have to subtract. So the minus x squareds disappear, of course, which is what we need to happen. We're gradually reducing the powers of x that we're dealing with, and minus 2x take away 6x is 4x. We then bring the 6 down, so we're now dividing x plus 6 into 4x plus 6. So we need 4 times x plus 6 to get rid of the x's. So we have plus 4 and then 4 times x plus 6 is 4x plus 24. When we subtract that, we have minus 18, and we can't divide x plus 6 into that, so that is our remainder. Now, as I mentioned before, there are other ways to do this, and you will see them later on, but for now, this is a method that works. So to reflect what we looked at with the numerical example on the left, we now have that x cubed plus 5x squared minus 2x plus 6 divided by x plus 6 is equal to x squared minus x plus 4 remainder minus 18. And of course the minus 18 still hasn't been divided by the x plus 6, so we could write that, instead of writing it as a remainder, we could say that we have x squared minus x plus 4 minus 18 still needing to be divided by x plus 6. And we can express the whole result as our original polynomial, x cubed plus 5x squared minus 2x plus 6 is equal to x plus 6 times x squared minus x plus 4, but we still have a minus 18 left over. If we think about the degree in this situation, the degree of our original polynomial we were dividing, x cubed plus 5x squared minus 2x plus 6, take away the degree of our divisor, x plus 6, is equal to the degree of the main answer that we've got, which is our x squared minus x plus 4. And that's a general rule as well that you can use to check things. Okay, now all this is leading us to a couple of very important theorems, and they are called the remainder and factor theorems. So we've just seen that if we do that division, x cubed plus 5x squared minus 2x plus 6 divided by x plus 6, we get this answer which we can write out. So we can write that division as a fraction, and it equals x squared minus x plus 4 take away 18 times x plus 6. And if we multiply by x plus 6, then we get the other result that we saw. So that's telling us that the original polynomial, x cubed plus 5x squared minus 2x plus 6, is equal to x plus 6 times x squared minus x plus 4 take away 18. Now, we're going to consider a more general situation now. So this is quite difficult, so don't worry if you struggle with this, at least at first, but we're going to look at p of x, which is a polynomial, hence using the letter p, and we're going to divide by x minus a, where a is just some number. And similarly to above, when we write p of x divided by with our usual division symbol, x minus a, we can write that instead as a fraction, so that's p of x over x minus a, and that will give us another polynomial, q of x, plus a remainder which still needs to be divided by x minus a. So that is similar to, in the above example, we had our x cubed etc. divided by x plus 6, and we got another polynomial which was x squared minus x plus 4, which is our equivalent to q of x, and then we had a remainder still needing to be divided by x plus 6. So in this more abstract situation we have a remainder still needing to be divided by x minus a. And I've mentioned that p of x is a polynomial and q of x is a polynomial, so that's just reinforcing that. P of x and q of x are both polynomials. Okay, now with this fraction version of our abstract situation, we can still multiply through by x minus a, and that will mean that the x minus a that's dividing the p of x and the one that's dividing the r will be cancelled out, but q of x will be multiplied by x minus a. And that leads us to the remainder theorem. If we put x equals to a into that last equation, then instead of p of x equals x minus a q of x plus r, we get p of a equals a minus a q of a plus r. of course, a minus a is 0, as it always is. So we're left with p of a equals r. And this is giving us the remainder theorem. So the remainder theorem says when a polynomial p of x is divided by a linear expression x minus a, the remainder will be p of a. And notice it's x minus a. And if you ever are wondering when you're using this, oh, is it x minus a or is it x plus a? If you remember that in the derivation of it, it works because if you look above, where we have the line p of a equals a minus a, it's because that came from putting a into x minus a that we end up with 0, and therefore we can get rid of q of a altogether. So that's a way of remembering that it's x minus a within the remainder theorem. Okay, it also leads us to the factor theorem. And the factor theorem says that if we have this situation of dividing p of x by x minus a, then if there is no remainder, then that tells us that x minus a must divide exactly into p of x. And that tells us that x minus a is a factor of p of x. Okay, so if we state the theorem, if for a polynomial p of x we know that p of a is 0, then that tells us that x minus a is a factor of p of x. Now, practically speaking, this is really useful for factorizing polynomials.